A minimum spanning tree, MST, is a way to connect all the points vertices of a graph with the smallest possible total length weight. Imagine you have a set of islands and you want to build bridges so that you can travel from any island to any other island, but you want to spend as little money as possible. The bridges are the edges, their costs are the weights, and the set of bridges you finally choose is the MST. Electric power grids, connecting cities with power lines while using the least amount of cable. Computer networks, laying fiber optic cables between servers to keep the total length short. Road design, building a road network in a new park, so every trail can be reached without unnecessary loops. Clustering in data mining, an MST helps to group similar items by cutting the longest edges. Mathematically, given a connected undirected weighted graph G with vertex set V and edge set E and weight function W from E to positive real numbers, an MST is a subset T of E such that the graph with vertices V and edges T is a tree with no cycles, and the sum of the weights of the edges in T is minimum among all possible spanning trees of V. Prim's algorithm works like a greedy treasure hunt. Start at any city vertex and always take the cheapest bridge edge that leads out of the part of the map you have already explored. You never look ahead far, you just pick the cheapest next step. This greedy choice works because every time you add the cheapest possible edge that connects a new vertex, you are sure you are not creating a cycle and you are keeping the total cost as low as possible at that moment. Why do we need this greedy rule? Imagine you tried to connect the islands by randomly picking bridges. You could end up with a very expensive set or even a loop that does not help you reach new islands. By always choosing the cheapest outward bridge, you guarantee that you are building the cheapest possible frontier of the tree, and that frontier will grow until every vertex is inside the tree. Think of it like filling a puzzle. You already have a piece, and you always attach the piece that fits best the cheapest to the current shape. This simple rule is enough to give the optimal solution for MSTs, thanks to the special property of cuts explained later. Formal description. Input a connected undirected weighted graph G equals V, E with weight function W. Output a set T of edges forming a minimum spanning tree. Pseudocode. Prim of G, RR is any start vertex. For each V and V initial K's are infinity. Key of V gets infinity. Parent of V gets nil. Key of R gets 0, start vertex gets key 0. Q gets V priority Q keyed by key. While Q is not empty, U gets extract min of Q vertex with smallest key not yet in tree. For each U, V, in adjacency of U examine neighbors of U. If V is in Q and W of U, V is less than K of V. Parent of V gets U. Key of V gets W of U, V. Decrease K of Q, V, K of V. Return the set of parent of V and V where parent of V is not nil. Edges of the minimum spanning tree. Explanation of variables. Key of V stores the cheapest weight of an edge that can connect V to the current tree. Parent of V remembers from which vertex V was reached, so when the algorithm finishes we can list the tree edges. Q is a min priority queue that always gives the vertex with the smallest key value. The algorithm stops when all vertices have been pulled out of the queue, meaning every vertex is now part of the spanning tree. Explanation. To show that Prim's algorithm always gives a correct MST, we use the cut property. A cut is a partition of the vertices V into two non-empty sets S, and V set minus S an edge that goes from a vertex in S to a vertex in V set minus S is said to cross the cut. The cut property states, if an edge E has the smallest weight among all edges crossing a cut, then E belongs to some MST. Proof sketch for Prim. 1. At any step of Prim, the vertices already inside the tree form a set S. The algorithm looks at all edges that leave S. These are exactly the edges crossing the cut SV set minus S. 2. Among those crossing edges, Prim picks the one with minimum weight, call it E star. 3. By the cut property, E star must be part of some MST. Adding E star to the current tree cannot create a cycle, because the other endpoint is still outside S. 4. Repeating this argument for every iteration builds a tree consisting only of edges that belong to an MST. Therefore, the final tree is an MST. The key idea is that each greedy choice respects the cut property, guaranteeing optimality at every step. For a formal proof, one can assume a contradiction. Suppose the algorithm's tree T is not minimum. Replace in an optimal tree the first edge where T and the optimal tree differ with the cheaper edge chosen by Prim. This never increases total weight, leading to a contradiction. Explanation: the running time of Prim's algorithm depends on how we store the graph and the priority queue. Data structures. Structure for Q vertical bar update operations: vertical bar cost of extract minus min vertical bar cost of decrease minus key vertical bar overall time with vertical bar v vertical bar equals n comma vertical bar e vertical bar equals n. Separator line of the table. Simple array slash list vertical bar O of 1. Just assign vertical bar O of n. Scan all vertical bar O of 1 vertical bar O of n squared. Good only for dense graphs. Binary min heap vertical bar O of log n vertical bar O of log n vertical bar O of log n or O of log n amortized. Vertical bar O of m log n works well for sparse graphs. Fibonacci heap vertical bar O of 1 amortized. For decrease minus key vertical bar O of log n vertical bar O of 1 amortized vertical bar O of m plus n log n, theoretically fastest, but larger constant factors. A space usage. The adjacency list representation of the graph needs O of n plus m space. The priority queue stores at most n keys, so another O of n space. Arrays key bracket bracket and parent bracket bracket also need O of n. Overall, Prim uses O of n plus m memory, which is linear in the size of the input. What about dense graphs? When m approximately n squared, almost every vertex is connected to almost every other vertex. The O of n squared version with a simple array becomes competitive because n squared dominates m log, and that is why textbooks often present two versions, one for sparse graphs heap and one for dense graphs array. Explanation: the fastest practical implementation combines an adjacency list representation with a binary heap or a pairing heap, which behaves like a Fibonacci heap in practice. Step 1. Build an adjacency list: for each vertex store a list of pairs neighbor comma weight. This allows us to iterate over only the edges that actually exist. Step 2. Initialize a binary min heap queue that holds all vertices keyed by their current key value. Initially, the start vertex gets key 0, all others get infinity. Step 3. While Q is not empty, pop the vertex U with smallest key. This vertex is now part of the minimum spanning tree. Step 4. For every neighbor V of U found by scanning edge of U. If V is still in Q and the edge weight W of U, V is smaller than the current key of V, update key of V and parent of V and call decrease key of Q V W of U, V. Extract min costs big O of log n because we remove the root and ray heapify. Decrease key also costs big O of log n because we move the updated element up the heap. The total number of decrease key calls is at most m once per edge, so the overall time stays big O of m log n. Keep an auxiliary array pose of V that remembers the current index of vertex V inside the heap. This makes decrease key big O of log n without searching. Use zero-based indexing for arrays to match typical programming languages. When the graph is dense, replace the heap with a simple array of keys, and find the minimum by scanning the cost becomes big O of n squared, but avoids heap overhead. Result: with adjacency lists plus binary heap. We get a clean, memory-efficient, and fast implementation suitable for most real-world problems such as road network design or network routing tables. A connected to B with weight 4, B connected to C with weight 2. A connected down to D with weight 3, B connected down to E with weight 5. C connected down to F with weight 1, D connected to E with weight 6, and E connected to F with weight 7. Initial state: key of A equals 0, all other keys equal infinity. The priority QQ contains A, B, C, D, E, and F. All parent pointers are nil. Step 1. Extract minimum gives A with key 0. Add A to the minimum spanning tree. Inspect edges from A. Edge AB has weight 4, so update key of B to 4 and set parent of B to A. Edge AD has weight 3, so update key of D to 3 and set parent of D to A. The queue now holds keys B equals 4, C infinity, D equals 3, E infinity, F infinity. Step 2. Extract minimum gives D with key 3. Add edge a dash D to the minimum spanning tree. Look at neighbors of D. Edge D. E has weight 6, so key of E becomes 6 and parent of E becomes D, which is smaller than infinity. Step 3. Extract minimum now gives B with key 4. Add edge a dash B. Examine neighbors of B. Edge BC has weight 2, so key of C becomes 2 and parent of C becomes B. Edge BE has weight 5. The current key of E is 6, so replace it with 5 and set parent of E to B. Step 4. Extract minimum gives C with key 2. Add edge B dash C. Look at neighbors of C. Edge CF has weight 1, so key of F becomes 1 and parent of F becomes C. Step 5. Extract minimum gives F with key 1. Add edge C dash F. Check neighbors of F. Edge FE has weight 7, but the key of E is already 5, which is smaller, so no change is made. Step 6. Extract minimum gives E with key 5. Add edge B dash E. All vertices are now included in the tree. The resulting minimum spanning tree edges are a dash D with weight 3, a dash B with weight 4, B dash C with weight 2, C dash F with weight 1, and B dash E with weight 5. The total weight is 3 plus 4 plus 2 plus 1 plus 5 equals 15. Visualization of the order of addition. First A as the start vertex. Then D added via edge a dash D with weight 3. Then B added via edge a dash B with weight 4. Then C added via edge B dash C with weight 2. Then F added via edge C dash F with weight 1. Finally, E added via edge B dash E with weight 5. Explanation: both Prim and Kruskal produce a minimum spanning tree, but they work differently and excel in different situations. Aspect: Prim's algorithm, Kruskal's algorithm. Basic idea: grows one tree by always attaching the cheapest edge that connects the current tree to a new vertex. Kruskal sorts all edges by weight and adds them one by one, skipping any edge that would create a cycle using a union-find structure. Data structures needs a priority queue keyed by vertices heap. Kruskal needs a global edge list sorted by weight and a disjoint set union DSU. Best for dense graphs many edges, when an adjacency list plus binary heap gives big O of m log n or even big O of n squared with an array. Also useful when you start from a specific source vertex, for example building a network from a central hub. Sparse graphs few edges with a binary heap big O of m log n graphs that fit easily in memory and you can sort edges quickly. The graph is given as an adjacency list, and you want to avoid sorting all edges. You have a natural starting point, like a power plant, and want to expand outward. The graph is dense. The big O of n squared version may be faster than sorting m edges, which could be approximately n squared as well. The edge list is already sorted, or can be sorted once and reused for many queries. You need to handle a forest, multiple disconnected components, and want a minimum spanning tree for each component. Implementations that rely on DSU are often simpler and have lower constant factors for very sparse graphs. In short, if you think of building a network starting from a central station and expanding outward, imagine Prim as a growing fire that always spreads through the cheapest fuel. If you think of connecting cities by looking at all possible roads first and then picking the cheapest safe ones, Kruskal is like a builder laying down roads one by one while checking that it never makes a loop. Prim's basic idea can be tweaked for special cases or to run faster on modern hardware. 1. Dense graph version no heap. When m approximately n squared, using a binary heap gives O of m log n, approximately O of n squared log n, which is slower than the simple O of n squared array version. Implementation: keep an array key, and each iteration scan all vertices not yet in the tree to find the minimum key. This costs O of n per iteration to total O of n squared. Good for small to medium graphs that are almost complete, for example fully connected road maps. 2. Parallel Prim. The main bottleneck is finding the minimum key across the frontier. In a parallel setting, you can split the vertex set among processors, each finds a local minimum, then a global reduction picks the overall minimum. After adding a vertex, updating the keys of its neighbors can also be done in parallel, because each neighbor's update is independent. Parallel overhead is modest for very large graphs, millions of vertices, and can achieve near linear speedup on multi-core machines. 3. Variance for special weight functions. If all edge weights are integers in a small range, you can use a bucket priority queue Dial's algorithm to achieve O of m plus c where c is the maximum weight, often linear. 4. Prim on a minimum bottleneck spanning tree. Sometimes we care only about the largest edge in the tree, the bottleneck. Running Prim and then taking the largest weight among the chosen edges yields a minimum bottleneck spanning tree, which is useful for designing networks where the weakest link determines performance. 5. External memory I/O efficient Prim. For graphs that do not fit in RAM, store adjacency lists on disk, and use a buffered priority queue that batches decrease key operations, reducing disk seeks. 6. Using Fibonacci heap. Theoretically gives O of m plus n log n time, which is optimal for sparse graphs. In practice, the constant factors complex data structure often make binary heaps faster, but for academic purposes the Fibonacci heap shows the power of amortized analysis. Summary of when to choose variants. Simple array O of n squared. Very dense graphs small n or educational settings. Binary heap O of m log and general sparse to moderately dense graphs. Fibonacci heap O of m plus n log n extremely large sparse graphs where theoretical limits matter. Bucket queue integer weights with small range. Parallel or distributed, huge graphs on multi-core or cluster systems. External memory, graph larger than main memory. These extensions let Prim stay useful across a wide spectrum of real-world problems, from tiny classroom examples to massive internet-scale network designs.